Thanks very much. There's a song called Things to Do in Denver When You're Dead. Has anyone ever heard that? Yeah, cool. So that's where I was inspired to come up with the particular title for this talk, Things You Might Like to Know About Metrics. But it is an accurate summary of what I'm trying to achieve here in the next 45 minutes. So I historically haven't had a lot of exposure to metrics for application telemetry up until fairly recently, and then it's really all I've been doing for the last 6 months or so. So what I thought I'd try to do was, in 45 minutes today, try to tell you the interesting things about metrics that'll help you to know if it's something that you even care about or something that you might be able to use in your systems and get some value out of. So that's the plan. We did have a little bit of technical difficulty, so I don't have my notes, but I'm sure we'll be fine. We've all heard several times today about our great sponsors and thanking them. As I understand the way that DDD works, it isn't so much the ticket price that pays for the event as the sponsors. So in a very real sense, they are the only reason why these events happen. So I want to say thank you to them, as usual. And so it turns out that logs are all you really need for application telemetry. So if we think about, say, like the human body, we might want to record our heart beating. So a heartbeat is an event. It's a thing that happens at a particular moment in time. And at that time, we can construct an event and we can say, Liam's heartbeat, when that happened, we might record some other interesting data about it as well. So, for example, the complete duration of the muscle contraction, what was the maximum blood pressure, things like that. Whatever it is that we think is interesting about a person's heart beating, we can record that that event happened at a particular moment in time. And that is the true, accurate, and complete record of reality, of history, of the thing that actually happened. And that's what logs give us and why logs are the most useful application telemetry. If we wanted to know, say, heart rate, which would be a metric, then we can always derive heart rate from that original log event data. We just count them up and we divide them by however much time we have, and that would give us a heart rate. So we typically can always derive metrics from logs, and therefore we don't need metrics at all. But the problem with logs is that they don't scale. If you think about my heart beating, which I don't do very much, think about it, not have a heartbeat, it happens however many thousand times a day, and if we were to record every single one of those as a log event, it's a terribly boring data set. And that's just like something pretty simple. I was thinking about the case of my car. So if you have a reasonably modern car, it's full of computers. They tell me that a new car has somewhere between 30 and 100 individual ECUs in it. And if we wanted to understand what was happening inside of that vehicle, we would need to be collecting log data from every single one of those, of every single activity that they're undertaking at any moment in time. And then you might be like a business with a fleet of cars. So you've got 100 ECUs times 100 cars. You've got 10,000 of them producing logs. Or maybe you're an insurance company and you've got 1 million cars that you're tracking. No matter what it is you're doing with log data, there's always a way to scale so that it doesn't work anymore. So the point is, and probably the number one takeaway, the only reason that metrics exist is as an optimization. It's a way of condensing a very large data set into a smaller one that contains more of what we care about and less of what we don't. Metrics are quantitative data that describe the behavior, health, and performance of a system. Or a simpler definition that I prefer is to say metrics are numbers that change over time. pretty much accurate. So you can think of it, or you could model it as a list of pairs of timestamp and value. And in that sense, they're also a time series. As a fun recent example, you might have noticed recently Cloudflare had an outage and a bunch of people's websites stopped working. When that happened, they went to their telemetry system and they got this chart of HTTP 500 errors. It's a count against time. And so you can see that there's background noise of errors that are occurring all the time, but then at some point, something goes horribly wrong. So because they had this telemetry data, because they had these metrics, they're able to see that they're experiencing an abnormal event. And another thing that you'd be tempted to do if you worked at Cloudflare and you were responsible for keeping the network running, you might want to establish some kind of alerting, even if it was quite high, maybe like around 10 million error status codes per second. You might say, if we ever hit that threshold, something's very wrong and I'd like to know about it. So that's the typical kind of thing that you would do with metrics. And if you've ever worked with AWS or Azure or Open Task Manager, pretty much any time you have a chart that looks like that, then we're looking at someone's metrics. Okay, now contextually, these things exist in a larger system. So within some kind of context, we might have a software system. We might also have some hardware systems. Both of these can be producing metrics and feeding them into a metrics database of some description. The most famous of these is Prometheus. Do you have any Prometheus users? Yeah, cool, okay. So Prometheus is pretty much just a database for storing metrics. Once we've got them merged together and collected into a database, we can look at doing things like evaluating queries over that data set. When you do that, you kind of get back numbers that are pretty hard to interpret. So the first thing we normally want to do is then produce visualizations from our query results. It turns out that for some sort of evolutionary reason that I don't understand, people are very good at detecting patterns in visual images. So we get a lot of value out of visualizing our metric query results. And then the other thing is alerts. So pretty typically, most metrics exist within some range that we consider to be normal. So we might like to be notified when they stray outside of that range. Okay, so Formula One, it's a space that's really interested in telemetry in particular and metrics. So I want you to imagine that, like Niki Lauda, you've just purchased your own Formula One team. You're going to be competing next season. And before the season starts, you want to take your cars and you want to get them out on the test track and make sure everything's working properly and you're going to be competitive next season. So if that were you, what metrics do you think you might like to collect about your Formula One cars? Yep, for sure. Engine performance. So maybe something like the power output, something like that. Yeah. Pardon? Fuel consumption, for sure. So we could track fuel consumption. So fuel consumption is an interesting one because that's a rate. So it might be a metric that we would derive by tracking the amount of fuel remaining in the fuel tank. And as that counts down, we can look at that over time and determine a rate and decide if that's within our kind of range that we think is acceptable. Anything else? Drag? Yep. Probably hard to test on a racetrack, but maybe you could do some like wind tunnel testing and collect data out of that. Yep, absolutely. And G-force. G-force is a cool one. Also probably a wind tunnel type of situation, but yep. Lap times, yep. So that's not to do with the car, but absolutely, like in terms of like, if we broaden the system, we're thinking about from being just the car to being the car and the driver and that overall performance, then things like lap time, reaction time when the light turns green, all that kind of stuff might matter. Yep, speed, brake temperature, engine temperature, coolant, lots of different temperatures, basically the temperature of everything. But those are good examples. And so it's really easy to think about the kind of metrics that we might want to collect. It's slightly more difficult if I say, why do we want to do that? What value are we going to get out of collecting all that data? Any thoughts? Yep. So I suppose we might go through a process of optimization where we measure, we look at the results, we might interpret the metrics that we get and make a hypothesis about a way that we can prove it, make the change, put it back out, test it again, that kind of thing. That's pretty typically the kind of thing that we try to do with metrics. Okay, so you got the hang. And I said before that people are really good at looking at visual things and detecting patterns, working out what doesn't fit, and just generally interpreting fairly complex signals in data. So I want to play a game where I show you some metric visualizations. So these are real metric visualizations from real Formula One cars with real drivers on a real racing track. And what I've done is I've stripped off the axes and the labels. So all you get is the shape of the chart. And the game is you have to try to guess what the metric is. Ready? Here we go. Any idea what this represents? Revs, that's a good guess. We can see it kind of going up and down over time, so that fits with revs, but it's not revs. Acceleration, also very good and very close. Speed. Okay, so this is speed. Exactly right. We know this is speed because it has this shark tooth pattern where the quantity increases rapidly, and then the higher the quantity gets, the slower the rate of change. So that's happening because the drag on our Formula One car increases with the square of velocity, so you get this kind of shape. Awesome. Okay, what about this one? Gear, exactly. And how do you know that's gear? It's because it's discrete. So it has two interesting properties. One is that it's discrete. It jumps up in quanta. Its other property is that it very rarely ever actually skips a value. So pretty much it goes up in single steps and it goes down in single steps. That's the gear that the car is currently in. Okay, so this one is obviously a pair of charts that I've included here. Just looking at the shape of it, what features can you see in these charts? They're contradictory. They're sort of like the mirror of each other. When one is high, one is low. Throttle and brake. Yep, exactly. So the driver is always, he's either trying to go faster or he's trying to go slower. And that's that one. What about this one? Tricky. No, I think someone might have said it. Not acceleration, it's not fuel, it's... So again, we can see sort of like a little bit of a sawtooth pattern in there. I think, yes, if I pair it up with this chart, so often when we're trying to interpret metrics, what we're doing is we're correlating with other metrics in time. So we might have this kind of situation where just by looking at that first chart, it's very hard to interpret. But if I add the second one, It's revs. That's exactly right, yep. So that's him going up through all the gears as Formula One cars do. Yep, so that's the full chart, the full dashboard. Also, because of the value of looking at sets of metrics together and trying to see how they correlate, we often end up with kind of dashboardy type scenarios where by themselves the metrics might not tell us all that much, but when we look at them, the right ones side by side, then we can detect a signal. Metrics are essentially always aggregated, so we're always talking about some kind of summary of the data. And as with all summaries, that means that we're throwing away some information in the hopes that what we're left with is the interesting part. The most common aggregations that you'll use with metrics are these 6, count, sum, mean, min, max, and percentile. But there's hundreds of them that are available. But the trick is always to make sure that the aggregation you're looking at is the one that's most appropriate to the context. And it's not always obvious what that is, but different summaries will produce different patterns, and you have to be sure you're always using the right one. Here we have a sample of values. This is the kind of thing that your metric might produce. And then aggregations are functions, as I said, that summarize a set of values and boil it down to one value. So in this case, we've got the mean, the min, and the standard deviation. Those values are correct for this set of numbers. And what you can see is that whilst I have 3 different summaries of the same input, they're all very different. 43, 3, and 31. There's no commonality. There's no pattern there. They're all correct summaries, but they're summaries that are looking for different things. So mean's an easy one to understand, and you know why we might commonly use that one. If you were monitoring like the level of a drinking water dam or something, then maybe the minimum aggregation might be the one that you would track. And if you, for some reason, cared about the variation in your sample, then standard deviation is the one for you. So it's just a matter of picking the most appropriate summary for your particular context. All telemetry data has a data model, and we've gone through a bit of evolution, really starting, in terms of application telemetry, really starting with this kind of text-based log file. This is a log from an Apache web server. So every time some event happens in the system, we append a new line to a text file. It starts with a timestamp that tells us when the event happened, and then it's followed by a bit of text. So that's kind of like the simplest model that we've ever had. If you've got a bunch of different systems, you end up with this scenario where when something breaks, you've got to go collect all the text files and print them out and line up the timestamps and try to work out what was going on. But all the information's there, so you can do that. So we could represent the data model of this kind of log data in this way. So for every log event, we have a timestamp and we have some kind of message. If we're a little bit more sophisticated with our logging, then maybe we add a log level in there as well to tell us if this is an informational event or a warning or an error, as the case may be. We still have the human-readable text message part, but perhaps we also attach a set of key value pairs with related metadata. It turns out that when you do that, those key value pairs become very useful for searching through your log file. It's often those that you're searching by, and they're also very useful for grouping up things so you can do analysis. And that comes up especially with metrics because we're always aggregating. So when you aggregate, you firstly have to group the data and produce an aggregate for each group. The metric data model then is very similar. So we still have a timestamp. It's still a time series. the message is gone, but now we have a metric sample value, and we also have that attached set of key value pairs. Historically, the terminology has been to call them labels, so I believe that's the Prometheus terminology. More recently, I think in the OpenTelemetry world, they call them attributes or sometimes dimensions, but it's all the same thing. Okay, so metrics come in a number of different flavors. The first one of them is a counter. A counter is a metric that's a numeric value that can be incremented or decremented. If the counter goes in one direction only, so only up or only down, then it's called a monotonic counter. Examples of things like counting the number of web requests we've received, counting the depth of a queue. So queue depth is an example of a non-monotonic counter because it can go up, it can go down. Its only constraint is that it can't be less than 0. The numbers of errors that have occurred, we could track that as a counter. At the kind of business application telemetry level, you might count the number of products that have sold or the total value, those kind of things. Those are counters. And then typically we would look at them as a chart like this and see a line that goes up. All right. So I've got a little .NET program here. It has two components. It's got a little web server, which is a weather service. You send it a postcode and it tells you what the weather is. So I've got that one. I can start up. So this is, when the service starts, it's printing to the console a bunch of metric stuff. So this is all the startup metrics. And then I've got another .NET program. This is just a little CLI program that I can pass the postcodes to. So if I ask for the weather forecast for postcode 4000, in addition to all the output from the metrics, that's the actual output of the program there. It tells me it's 24 degrees in Brisbane at the moment. If I change that postcode to like God's country, this one's a postcode that it doesn't know about, so it's an error. So if I then look in my metric database, here I have a dashboard. It's tracking metrics produced out of that application that we just ran. So every time it receives a request, it either successfully finds the postcode, in which case it increments the found postcodes counter, or it fails to find the postcode, in which case it implements the missing postcodes counter. This is where the metrics are defined. So we start with a meter, which is a thing that can create metrics. So I've got a meter for my example weather service web application. And then from that meter, I can create metrics. The first one I create is a counter, and it has a type as well. So in this case, we're using unsigned 64-bit integers. You give it a name, a unit, and a description. I've got one for found postcodes and a counter for missing postcodes. Then when the program runs, if it successfully finds the postcode, it adds 1 to the found postcodes counter. If it fails to find the postcode, it adds 1 to the missing postcodes counter. That's counters. The second type of metric is gauges, also a number that changes over time. But gauge is kind of like the pure metric in that all it is a number that changes over time. So it has no attached semantics. There's no rules. It's just, you just can give it whatever value you feel like at any point in time. This metric here, random value, is a gauge. So it's created as a gauge, name, value, description. And then instead of having an add method, it has a record method where you just give it a value. So an interesting thing about gauges in this sense is that the signal that you take out of looking at that metric depends when it's sampled. So if you think about like if we had a gauge for a sine wave, if you sampled the value in the same frequency as the wave, you would just get a flat line, even though that's not actually the shape of the data. So this application includes some logging as well. So for example here, I'm creating a log event. Every time that part of the program runs, we create a log event, we put it goes into a queue. It's in the sort of logging library that I'm using, and then on some particular frequency that queue gets processed, and the log event that I created, pretty much as I created it, is sent off to a server somewhere. So if you think about an application that does something in like a really tight loop, if we wanted to log in that kind of scenario, we have this problem that on a really high frequency, if you're creating these log events and processing them through a queue and sending them off, it's very easy to get into a situation where pretty much all your application's doing is logging. That could be the vast majority of the resource consumption. If, on the other hand, we're in a tight loop, and every time we go around, we're recording a value for a gauge or we're incrementing a counter, the only work you're actually doing is changing one number in memory, which is nothing. And then on some other frequency, there's some other part of the system that samples that value you send and processes it. But that happens on a much lower frequency. So that's really the secret for the way that metrics can be used to reduce the cost of telemetry collection within your application. There's two sides to it. There's that telemetry collection side, and then there's the server-side processing. And on the server-side processing, there's advantages to metrics as well, because they have a schema, we know their numbers, they can be packed very efficiently and processed very efficiently. So the process of querying them and producing charts and things is much more efficient than if we were to try to do the same thing by calculating those metrics on the fly from log data, for example. The third common type of metric is summaries or histograms. So all metrics are aggregations, they're all summaries, but the histogram type takes it even further. If I told you that the average rainfall in Sydney is 1,200 millimetres per year, that would mean that on any given day in Sydney, the average rainfall is 3 millimetres. But if I asked you and I said, given that information, is it going to rain tomorrow? You don't have what you need to answer that question, because all you know is the summary across the entire year. It doesn't give you any information about what might happen on a given day. But if we have a histogram like this one, which shows the distribution of rainfall in Sydney, now it's a very different story. So this is the rainfall for Sydney for 1 year. So looking at that histogram, if I said, place a bet, is it going to rain in Sydney tomorrow? What would you say? Pardon? It's very close to 50-50. So 50-50 is a good guess. The very leftmost bar there represents days that have no rainfall. So and it's about 160. So this tells us that 160 days a year it doesn't rain in Sydney, which means 200 days a year it rains a bit. And on the days when it rains, it's pretty much a sort of an equal probability that it'll be somewhere between very little rain and 50 mils, a hell of a lot of rain. So by using histograms, we can very efficiently capture the distribution of numeric values. Really, that's essentially the point. With my sample set of numbers and a timeline, sorry, not a timeline, a number line. So I split the number line that contains all of those values into sections that are 20 wide. The histogram process then is about organising the numbers from the sample into the range that they fall. So between 0 and 20, we've got those three numbers. Between 20 and 40, just one, and so on. Having done that, the histogram is then created by drawing a bar. Its height represents the number of samples that fall within that range. So a histogram for that data set looks like so. And that works pretty well, and that's one kind of a histogram that you will see in telemetry data. The thing that I have not enjoyed about working with metrics is, unfortunately, where like logs and things are really straightforward. You just create your log and send it off, and that's all you have to worry about. Metrics push back a lot of cognitive load onto you, the user. It's like I've already talked about the fact that you've got counters, gauges, and summaries. The fact that you have to know that is a bit of a problem. And unfortunately, it gets even more complicated. I quite like this diagram of it's a seismometer, I think it would be called. It's a device that records the intensity of the ground shaking. When the earth moves, the weight swings, and it draws a line on a rotating drum. The more violent the movement of the earth, the larger the amplitude of the wave that gets drawn. And an interesting property of earthquake magnitude is that it varies across a very wide range. It's common to have earthquakes that produce amplitudes of 0.1 millimeters all the way up to and beyond 100 millimeters. So we've got 3 orders of magnitude there that we need to be able to represent. If we wanted to record in our application a histogram that spanned that range, we would have a problem because it would be very hard to know what size to use for the buckets. To be able to tell the difference between a 0.1 millimeter earthquake and a 0.2 millimeter earthquake, we would need very small buckets, which would then mean that we'd have 10,000 of them, which is too many to work with. On the other hand, if you wanted to be able to record your 100 millimeter earthquake, then maybe we'd use, say, 10 millimeter buckets, and then we lose all the resolution at the low end. There's an additional problem with this kind of histogram, which is for this 20 to 40 bucket, the midpoint is 30. So that's essentially the average value of items in that bucket. And that means that if our actual sample is 20, then we've got an error, which is the difference between the midpoint of the bucket and that value of 20, and the same for 40. So the maximum error value is always half the width of the bucket. If the sample you're recording is up at 10,000 and your maximum possible error is 10, and that's a very small relative error, and it's fine. But for that bucket between 0 and 20, because the maximum error is 10, that's half the width of the bucket. So you've got a 50% error, relative error at that point, which may be too much for your case. So what if, instead of doing that, we bucket values in a histogram in such a way that the first bucket looks like that, but then the second bucket is twice as big as the first one, and the next bucket is twice as big as that one, and so on. Each bucket twice as big as the previous one. This solves the relative error problem because the relative error across all the buckets is now the same. It also solves the problem of how do you deal with a very large spread of possible values. Because of the way that the bucket size increases exponentially, it's very easy to record a very large range in this way. And when you're recording histograms, you will have that option of whether you want to use fixed size buckets or whether you want to use those exponential buckets. The earthquake data ends up looking like this. So we've got quite a few earthquakes under 0.1 amplitude. Most of them are between 0.1 and 1, and then it kind of tails off from there. And each one of these groups is 10 times as wide as the previous one. This is a histogram of real earthquake data from the west coast of the US. So it's showing the same information. Here the buckets are the same width in terms of how they appear on the page, and also numerically. But this one is using the Richter scale, where the magnitudes are in base 10. So the magnitude of an earthquake of 4 on the Richter scale is 10 times as much as an earthquake of 3 on the Richter scale. So it's actually still an exponential histogram. It's just been rendered in a way to look linear. Once you have a histogram metric, the next problem is always how to visualize it when you want to split the data into different groups. So the most obvious way is just to draw a separate histogram for each group. And that works really well when you don't have very many groups, but as the number of groups go up, it just gets unwieldy to generate all the images. So another way that we can visualize histograms is with a boxplot. Here, each one of these columns is a group, so each represents a histogram. The bottom and top of the lines represent the minimum and maximum value. The bottom, middle, and top of each box is the 25th, 50th, and 75th percentiles, respectively. So by generating a box plot, we can easily visualize multiple histograms and get a feel for the distribution of values within each one. To go a little bit fancier, we can do a Violin chart. So it's the same thing, but each of the columns is effectively a histogram turned sideways and then reflected about the vertical axis. And these two show exactly the same data, just with two different visualizations. So by switching to the Violin chart, for example, for column B, we're able to see that this is a bimodal distribution with two separate peaks, whereas the boxplot kind of compressed that out. And we also can see things like that group D has quite a high peak, but all the values are fairly close together, whereas group A, there's much more variance. With telemetry data, the more common way of visualizing groups of histograms is as a heat map. Like the Violin chart, each column in a heat map is a histogram, turned sideways, and instead of representing the magnitude by the length of a bar, the magnitude is represented by the intensity of a color. So what this heat map is telling us, this one is grouped over time, so each column is a 5-second range. We're looking at 3 hours of data here. What we can see is that over the 3 hours, the distribution of values doesn't change very much. We have very little data between 0 and 8 milliseconds, and what's there is fairly randomly distributed. The main peak of values is around about 10 milliseconds, and it's very tight. Then we have an even spread from 10 milliseconds up to about 50 milliseconds, with the second peak, fairly diffuse peak between about 30 and 40. So anywhere you have tooling for dealing with metrics and histogram metrics, you're likely to come across heat maps. They're very useful. I mentioned Prometheus. The other option, I suppose, for telemetry currently is OpenTelemetry. So this is an open source project that implements some APIs for collecting telemetry and sending it somewhere. The idea being that if you instrument your app with OpenTelemetry, then you can send your telemetry data to any system you like, maybe multiple systems. Maybe you can change your mind over time and you don't get locked in with a particular vendor. That's the theory. It works kind of like this. So within your application, you might host the Hotel SDK. So that's an API for recording telemetry. And then wherever it is you want to send your telemetry to will likely implement the OTLP API. So that's a network API for telemetry. So then you can configure your application to send your telemetry off to wherever you care about. Because the OTLP API is a network API, you could in theory just send telemetry directly to it, but most of the time you don't. Mostly it goes via the Hotel SDK hosted in your application. Current sitch, there used to be projects called OpenCensus and OpenTracing. They're deprecated and folded into OpenTelemetry, which can do your logging, tracing, and metric telemetry. If all you care about is logs, then there's plenty of platform-specific libraries that you can use to achieve that goal. If all you care about is metrics, then Prometheus clients can do that for you quite nicely. But if you want to do all of those telemetry signals, then OpenTelemetry is probably the easiest way to go about it at the moment. Instrumentation is that process of actually collecting telemetry data. You have application code instrumentation, like this code that I showed you earlier. This is where we define our own custom metrics and collect them when the application runs. There's also library instrumentation. So the libraries you use, they already have that instrumentation in there. So when you set up the collection of metrics in your application, you'll automatically get metrics out of, in the case of .NET, out of things like .NET itself, ASP.NET, Entity Framework. Pretty much all the libraries you depend on will start publishing their own metrics. For example, so this is the list of metrics for ASP.NET Core. So there's one here called HTTP server request duration. It tells you its type is a histogram, its unit is seconds. Each sample, in addition to recording the actual duration of requests, you also get this set of attached metadata, the route, an error type if there is one, the HTTP request method, and so on. So these become the things that you're likely to want to search by or to group by. And it also tells you that for the histogram, these are the boundaries of the buckets that you're going to get. That's like a really good example, I think, of information that it's really unfortunate that you have to care about that because it's quite detailed, but that sort of is the current state that you do have to know that. There's also a thing called auto-instrumentation. So this doesn't involve adding dependencies to your application or writing any code. You just install something on your server and it magically starts collecting metrics for you. The way it does that is by doing things like monkey patching libraries, rewriting bytecodes. I've never used it because that whole concept kind of terrifies me of like having something just randomly start hacking into your application as it's running. But it does exist and some people like it. So in the case of logging, the .NET, the logging goes via iLogger and looks like this. And the kind of telemetry data that you get out of it is that combination of a timestamp, human-readable log message, and attached metadata. If you want to do tracing in .NET, it's done with the system diagnostics namespace and looks like this. You start a trace, start activity, and then call set tag for each bit of metadata that you'd like to attach to it. So it's a kind of ugly API, but it works. And then you can produce these sort of waterfall charts that show the different processes and the way that control flows between them. Or metric instrumentation, we saw that earlier. Create a meter, create metrics from your meter, record the values for your metric, and then you get a nice little chart out of it. So things you now know about metrics, what, why, and how. There's the feedback form, and do we have time for a question?
We actually don't, I'm afraid.
We don't? Oh,
apologies.
No worries. Okay, thank you.
Cool, round of applause for Liam, please, everyone.